Cary's going to be talking about how we can learn from plasma physics in the laboratory about plasma physics in the universe. And I think this is one of the most exciting things that's happening in plasma physics these days. So I'm looking forward to it myself very much. Cary, we go back, so I guess that's why I'm introducing him. Cary was born and bred in Madison, Wisconsin, and was an undergraduate at the University of Wisconsin in Madison. And then he went to Princeton, where Alex and I did our PhDs too. He was a PhD student at Princeton. I won't tell you the years because it's all getting a little bit too. After at Princeton, for your thesis, I remember, Cary, you worked on a small experiment about how to start a plasma without an electric field, which was quite an experiment. And what was characteristic of Cary's style is that he did his own theory as well as the experiment, which really is not allowed. We can't have experimentalists do theory.
Or vice versa.
Or vice versa. For his PhD, and then he went to General Atomics. And General Atomics is in San Diego, where they have one of the world's great fusion devices. And he distinguished himself at General Atomics with experiments in radio frequency heating, in performance of fusion plasmas, and he made quite a name for himself as a fusion plasma person, with regular visits to Germany and other places. But at some point, Wisconsin called him home. He was recalled to the place of his birth and the place of his undergraduate to become a professor in physics at University of Wisconsin, where he's led a group that both does fusion plasma physics and astrophysical plasma physics and basic plasma physics. And he has this phenomenal reputation really right across the field. The breadth is incredible. So also spectacular speaker. So, Cary.
That's a lot of pressure. Thank you so much, Steve. So today, I'll be talking about how we attempt in the lab to study processes we see in space. And these are things that have to do with magnetic fields. So with that, let me begin with this picture. So this is everywhere we look in the universe, we see plasma. That's how we see the universe. And often, almost always, it's magnetized. And this is a collection of images that I've picked up that illustrate that point. So over here we have a picture of the Earth's magnetosphere, actually a cartoon rendering. This is an image of the sun. The sun has a big magnetic field and a plasma that's around it. This is a pulsar emitting probably positron, electron winds from it with magnetic fields that go along, galaxy, jets, and perhaps even clusters of galaxies. And all of these objects are dynamos. And this phrase, if you haven't seen it before, this is a palindrome. So if you say it backwards, it's the same phrase. So dynamos goes both ways. In this talk, I'm going to try and give you a feeling for how magnetic fields are universal. I'm going to show you some of my favorite things about astrophysical observations of magnetic fields, and try to give you a sense that these are big, important things to look at. I'll give you a small tutorial on how dynamos work, and then I'll try and describe to you how, in the lab, we're studying some questions, some processes that are connected to magnetic fields in the universe. And I was going to talk about 3 problems, but I'm actually going to reduce that to 2 because I'm not going to have enough time to do everything. The first question will be, how do we search for and try and study self-exciting dynamos? And the second question has to do with how does matter accrete onto central objects like black holes? And these are 2 big questions. Where do magnetic fields come from? And how does matter accrete? And magnetic fields and the things I'll talk about are important here. So let me begin introducing astrophysical dynamos with, I'll try and define dynamos for you more carefully. The Earth has a magnetic field which is spontaneously generated by turbulent flows in the outer core. So the Earth, as you know, has a liquid metal core, and it's turbulent, it's convecting, taking the heat from the center, moving it outward. This creates flows. These flows act like an electrical generator to create magnetic fields. And this is the result of a numerical simulation which attempts to predict what this would generate, and it looks very much like the Earth's magnetic field. You have magnetic fields that stick out the North Pole and the South Pole, and this, the projector is not good enough to show this, I'm sorry, but if you looked at the detail of the lines in this region, you find that mostly they're pointing in the east-west direction. So it's a funny thing. Deep inside the Earth, the magnetic field is actually pointing east-west, and it sticks out at the poles in the north-south direction, as you know. Now, the Earth's field has been studied for a long time. You all know that it has chaotic reversals and so forth. What you might not have seen is something like this movie. So this is a movie which has been reconstructed from a set of observations made on ships for the last 400 years by naval sea captains, measuring the direction of magnetic north, and then eventually measuring things like the intensity of the magnetic field. And these measurements were made everywhere on the ocean, and it was an attempt to sort of map out what the magnetic field of the Earth looks like. And if you take that data, you can run it through a reconstruction algorithm that tells you what the magnetic field is at the core mantle boundary. So you can take the magnetic field that's measured, project it back to the core mantle boundary, and this movie, you can see, it starts in the 1600s, and again, let me start to show that again. So this is 1590, and you can see there are magnetic fields that stick out and point in, and it's not axisymmetric. It's not like you would think of just a simple Mar magnet, say, and it's time dependent. And this is representative of the turbulent motions in the core that are actually generating the geodynamo. So, is this turbulence important for the generation of the magnetic field? It turns out it is. And I'll try and give you a sense of how dynamos work a little bit later in the talk. If we look at the closest star, our sun, you can see immediately, if you look at something like the UV, the field lines that actually stick out of the sun. So the field lines are populated with plasma. The plasma emits light. We can then image it. So you get this, in the UV anyway, you get this image of very strong magnetic field lines that come up and stick out. And you get these active regions, which are sort of mid-latitude. These are where the sunspots are popping out of the sun. It's time dependent. If you look at it in detail, the satellites are providing some of the most amazing images I think ever taken now. This is a movie of a flare going off, and so magnetic fields, they're there, but not only are they there, they're also important because they do things like create the energy that ultimately gets released in the form of flares. And this is a super important problem that I would have addressed. It has to do with how does magnetic energy created by the dynamo and then converted into stored plasma energy and then eventually released as a solar flare. And that's a big question in plasma physics that would be worth having a whole talk about. So, but we're talking about the dynamo for now. This is another movie which is equivalent to the movie that I showed you for the Earth. So the yellow shows field lines sticking out, blue shows field lines sticking in, and these are measured using Zeeman slitting spectroscopy to measure the magnetic field strength. We can just take a picture of the sun and measure its time behavior. And this is now taken over the last several, maybe 3 decades. And what you find, so this is spreading it out over the latitude-longitude plane. And if you look at the behavior of these places where the field sticks in and out, you find that it comes and goes. So there's the 11-year cycle of the sun. And the polarity of these sunspots, so we're a yellow leading blue and blue leading yellow, flips every 11 years. So the sun's dynamo is a AC dynamo. The magnetic field is changing directions every 11 years. And it sort of comes and goes in intensity. Right now we're sort of at a maximum level of intensity. And if you average that out, if you perform an azimuthal average. So average the strength of the magnetic field in the east-west direction, and then plot that as a function of latitude. What you find is that there's a small dipolar field that exists, much smaller actually than the strength of the field in the sunspots, that switches directions every 11 years. And you see these sunspots emerging this so-called butterfly diagram, which describes the solar cycle, which is what the solar cycle is. So these movies are being made by very high resolution imaging of the solar surface using Zeeman splitting, measuring the polarized signatures of light coming from the sun. And you might ask the question, how about other stars? Did we learn anything about the magnetic fields from stars other than our own sun? So there are signatures. You can see things like flares, X-ray emission that pop up that we think are associated with the magnetic fields that come from other stars. But I want to show you something that's coming out right now, which I think is absolutely amazing, which is that people have invented a technique for actually measuring the field structure of stars, which are essentially point objects of light. So there's no discernible size to a star in the sky. There's light, there's emission that's coming from it. But the time history of the light emission coming in and its polarized signature and how it varies with time captures information about the spatial structure of the magnetic field on the surface of these stars. And this is kind of how it works. So if you look at a spinning star, and you imagine for a second that it's emitting light, and so there's stuff coming towards you and going away from you. So there's a Doppler shift to the light. And that can be measured as a velocity shift. So I'm characterizing this as the velocity coming towards you and then going away from you. So you can very easily measure the rate at which something is moving past you, especially if you have a big dark spot that rotates in front, right? Because this dark spot, you don't see it, now it's coming towards you, it makes it a little bit less emission, it goes around, and then you lose it. Okay, so there's information about where the spot is in your field of view. Now you can take this one step further, and you can measure something like, and then depending upon where it is, like if it's up here, for example, you get a little bit of effect, but not a super large effect. So there's information about the spatial structure. Now you can do something even more advanced, which is consider the polarization of the light that comes out. And when it's coming towards you from one side, the Zeeman split lines have a certain circular polarization that tracks where this magnetic spot is as it goes through your field of view. So it's Doppler shifted. That tells you which side of the star it's on, and then the intensity of this shift tells you how strong the magnetic field is, so you know where it is and how strong it is. And from this, and I'll just jump, you can actually reconstruct in 2 dimensions what the surface magnetic field is of these stars and build up catalogs now of what the structure is for a collection of stars. Just mind-boggling. Remember, this is a point source of light in the sky, and we're building up 2-dimensional maps of the strength of the magnetic field. So this is kind of the punchline. The size of these images. So this is the rotation period for the stars. So fast rotating stars are down here, 1 day to rotate. This is sort of where the sun is at about 29 days. And this is the size of the star in stellar masses. So low mass stars are down here, and the sun is up here. So this is our sun, and the size of the image represents the strength of the magnetic field which is created. Our star, it turns out, is a real wimp when it comes to producing magnetic fields. These low mass stars that are fast rotating, it turns out, are producing enormous magnetic fields. So rather than tens of Gauss, they're producing kilogauss and stronger fields. And there's information coming back. So it's a very exciting time for studying dynamos simply because we're making observations for the first time of what stellar magnetic fields look like. So a little bit further afield, for a long time we've been measuring the radio emission. The intensity tells you something about the strength of the magnetic field through synchrotron emission. And then the polarization of emission from galaxies, or the change in polarization from pulsars, which are illuminating it, can tell you the direction of the magnetic field and the intensity of the magnetic field. And so we know galaxies are also magnetized. And these vectors, which are superimposed on the image of emission from of this galaxy, are representing the spiral nature of the magnetic field that's created inside a nearby, this is M51, which is a nearby galaxy. So galaxies also have magnetic fields. So I think it's just to show you that magnetic fields exist on a multitude of scales. The final dynamo I'd like to leave you with is what I'll call an accretion disk dynamo. So this is an image where you have visible light showing a collection of galaxies. So this is an enormous object. These are galaxies, and this is the intergalactic medium. And in the center is a very strong galaxy with a black hole in the middle, which is very, very massive, accreting and active. And what it's doing is it's spewing out these jets of magnetized plasma and filling the intergalactic medium with radial lobes of magnetic field that are created deep down inside here on the accretion disk as part of a dynamo process. And so understanding that particular dynamo is super important for understanding how the intergalactic medium is actually filled with plasma. Now, this is, we know it's magnetized, we see that it's polarized emission, we can measure and estimate the strength of magnetic fields and so forth. There's a lot going on here. I'd like to call attention to one really interesting point, which is if you add up the rate at which magnetic energy and plasma energy is being created by this object, and you relate it to the matter, which is estimated to be accreting onto the central black hole, you can estimate how quickly and how much of the rest mass energy of the material which is accreting is actually showing up as kinetic energy or magnetic energy in these lobes that are being spewed out. And we estimate that this is as large as 10% of the rest mass energy of the material that's being converted continuously into plasma heat. Now, if you take that number and you take it at face value, 10% is an enormous fraction of the rest mass energy. If you compare that to fission or fusion, this is the most efficient conversion of matter into energy that we know of that's taking place in the universe. And so I think, what is the ratio of mass that gets converted in fusion energy, Steve? It's 0.1% or less, I think, right? So it's tiny. And this is 10%. So these are really important engines. Okay. So now let me try and describe to you how these systems work. And so I sort of alluded to this, but let me be a little bit more specific. So what are dynamos? Dynamos are systems which continuously convert kinetic energy into, in the form of some flowing plasma or perhaps liquid metal in the core of the Earth, into magnetic energy. And we'd like to be able to explain how these objects function. And the first person to ask this question was probably Larmor. And he asked the question in the following way. He said, how could something like a rotating body, I showed you that most of these systems are rotating, such as the sun, become a magnet? And his idea was it's possible for some of the internal motion to act in the manner of a self-exciting dynamo and create some permanent magnetic field at the expense of the kinetic energy of the circulation. Okay? And he used the term self-exciting dynamo because there were dynamos at that time. Dynamos were just electric generators. So in the 19th century, well, I'll come back to that. So let me describe how this might happen. I'll come back to that point in a second. So what is a self-exciting dynamo? So here's this is sort of the simplest possible model of a self-exciting dynamo. You're to think about this as a rotating copper disc that's spinning, and now you know that if there's a magnetic field present, this spinning disc, as it spins through the magnetic field, there will be an EMF which can drive current. And the current can then produce the magnetic field. And so physically, this is what that might look like. You have a disc which is spinning, and now imagine I have an electromagnet with a little tiny bit of current in it that creates this magnetic field. The V cross V of this going through the magnetic field creates an EMF from the center to the outside. So now you can hook this up with a brush to power the electromagnet. And if you hook it up in the right way, the magnetic field which is created by the current that's driven by this EMF actually drives more current in the magnet. If you hook it up the wrong way, it actually would reduce the field, and the field would actually go away. Now you can write down simple circuit equations for this system based upon the inductances of the coil, the rotation speed, the resistance of the material that makes up the disk, say, and a characteristic resistive decay time. And you can show that the current in this coil is governed by a simple linear differential equation. And the behavior of this equation is determined by this 3-factor out here. If this term is positive, you get growing magnetic fields. If it's negative, you get decaying magnetic fields. Now, if you take those parameters, which you can see immediately that this combination of parameters must be dimensionless. And I'll claim, I'll come back to this. These you can relate to units in the following way. Basically, this is a dimensionless product of permeability times the conductivity of the medium times the characteristic size times the speed that this disk is moving at. Okay? And this combination of parameters is really important for what I'll talk about. It's called the magnetic Reynolds number, and it's dimensionless, and it captures this idea that a system, a big magnetic Reynolds number, has some large size, it's very conducting, and it's fast flowing. And it's a triple product of those three things which makes the magnetic Reynolds number big. So in this particular case, if this number is big enough, bigger than 1 in this case, this system has an exponentially growing solution for the current. The current is producing a magnetic field, and we have a dynamo where magnetic energy is created at the expense then of some sort of kinetic energy in the disk. Now to show that, you need also an equation of motion, something that governs how the speed of the disk behaves. There's a torque that you apply to keep it going, and then there's a back reaction of the current flowing through the disk which makes it slow down. And so there's a process by which work is being done by the disk on the magnetic field, taking energy and converting it into, taking kinetic energy and converting it into magnetic energy. Okay, so this is a disk dynamo, and disk dynamos are used routinely, or the essence of the disk dynamo is used routinely to produce power. So the first person, so Werner von Siemens invented the idea of a self-excited dynamo in the mid-1800s. And before this time, people used permanent magnets and moving electrical disks to create currents. Okay, so in that case, the permanent magnet was the seed field, and then you simply got some power out because you had a disk moving through the permanent magnet. Now the permanent magnets were limited in strength, and this limited how much power the generators could produce. Siemens' idea was, well, why don't they take a little bit of the current which is being generated and create the magnetic field that you need in the first place to close the feedback cycle, essentially making the disk dynamo. Now he did it with iron and insulators and solid conductors, and he had a rotating armature down the center, but nonetheless this thing was able to generate its own magnetic field without using any permanent magnets, and that was the first time. Now this actually brought on the electric age. Without this, the amount of power which was available from generators was minuscule, and after this point, things as simple as telegraphs and then eventually electric motors and everything else became powerful enough to do important works. So let's take this object and let's heat it up until it melts. We'll strip away the insulators which are constraining the currents to flow in certain paths, and then somehow get rid of the permanent magnet, the ferromagnetic materials which cause the magnetic field to go in just the right place, and try to stir the mess that we're left with afterwards in such a way that you still get a magnetic field out of it. That's the problem we're now confronting for astrophysical dynamos. How do you do what this does in a homogeneous, self-connected, conducting fluid that is the plasma of a star or the inner core of the Earth? And that's a much bigger challenge, and that's why it's so interesting. Okay. So if you take Ampere's law and you take Faraday's law, and you take an Ohm's law, which relates the current to the electric field. You can combine them in such a way that you can eliminate two of the variables in favor of a single variable. And when you do that, you're left with what's called the magnetic induction equation. So you have to take it from me that what I've done is I've said that the electric field is equal to conductivity times the electric field plus the V cross B term. And I've gotten rid of the current in favor of the magnetic field, and I'm left with a single equation which governs the magnetic field vector itself. And this is what we use to describe how magnetic fields evolve in liquids which, or plasmas which have some flow. Okay? And this equation has two parts. It has the part which comes around because of induction. That's the part where if you have movement through a plasma through a magnetic field, you can create current. And then we have a second term, which is the diffusion of magnetic fields. So this is a part which is causing magnetic fields to decay away resistively in time. And the ratio of these two terms is just that magnetic Reynolds number that I showed you. So this is a dimensionless ratio of the induction term to the diffusion term. And when the magnetic Reynolds number is big, when the system is big, when the speed is high, when the conductivity is high, this dominates over this. Okay? That's the main point. In addition, you need an equation of motion which governs how the flow behaves. And this is the Navier-Stokes equation where you have acceleration of the fluid. The fluid is described by a vector velocity field, a mass density, a pressure gradient, and then you introduce the idea that there might be some Lorentz force which is acting on the fluid as well. And that comes about if currents are flowing across magnetic fields that give you a force on the fluid. Okay? So this is an equation of motion which governs how the fluid behaves, and there's a ratio of two terms I want to call your attention to here, which is the ratio of this term and this term. Okay? I want to think about systems, at least initially, where there is no magnetic field. Okay? And I want to think about systems where the magnetic field may grow up from nothing and become important. So if I want to study those systems, I'm going to require that this term be small compared to this, which is a requirement that the kinetic energy density of the fluid, so this is mass per unit volume times the flow speed squared, be much bigger than the energy density in the medium. And this regime of kinetic energy dominating over magnetic energy is a very special regime, it turns out, for experiments to operate in, especially if it's also where magnetic Reynolds numbers might be big. And I'll try and show you that. Okay? So in the limit where plasmas are flow dominated and the magnetic Reynolds number is big, this induction equation has a super interesting property, which is nothing more than Lenz's law in a moving conducting medium. Okay? And the idea is, if you ignore this term, you can think about magnetic field lines as being frozen into moving fluid. Okay? If the conductivity is big, magnetic field lines are going to get carried along and vectored by whatever the velocity is. So imagine you start with some seed field, which is just a magnetic field pointing up, down in a big conducting plasma. And now I start to push the plasma to the right in this region, so that in this region the flow is to the right. What will happen to these field lines is that they will get stretched out, and you'll create a strong field which is in the horizontal direction here, okay? And it'll be one direction up here, and it'll be the other direction down here. And this is really simple. So this is nothing more than the idea that in a very conducting medium, it's hard to change the magnetic field through a little blob of fluid. So it's Lenz's law applied to every fluid element in principle. And that's what this equation, that's how this equation functions. Okay, so this is probably one of the most important tenets of all plasma astrophysics. And so when we think about magnetic fields in space, the most important thing to remember is that basically the magnetic field lines are frozen into the moving fluid, whatever the fluid is, the plasma or liquid metal. Okay? From this, we're going to be able to construct dynamo models that make sense. Okay? That makes sense. So I'll talk about magnetic Reynolds numbers. I've been talking about those. In the Earth, these numbers are pretty big, something like 1,000 perhaps. That's the property of the liquid metal core. In the sun, it's getting very big, and in astrophysics, these numbers are enormous. So if you ask how well is the magnetic field frozen in, the first question you would ask is how big is the magnetic Reynolds number? And if this number is big, the magnetic field is frozen in well. Okay? So I tell you that the magnetic field is well frozen into galactic plasmas. Okay, and that's why. The fluid Reynolds number, I'm just going to tell you that the fluid Reynolds number is very similar, and it tells you something about the viscosity. It's very closely related. Size times speed divided by the viscosity. And this determines what the details of the velocity field are. So whether or not it's a turbulent flow depends on how big the Reynolds number is. Big Reynolds numbers, a 747 has a Reynolds number of 10 to the 7. It's a very turbulent flow around its wings. In astrophysics, the numbers get astronomically large. Right? Okay. So I'd like to show you now, I think, what I call the standard model for astrophysical dynamos. And so the question is, how do you start with something like a simply connected spherical body, like a star, and what sort of flows would be required inside the star that could create a magnetic field? And this principle I just showed you, the idea that a sheared velocity field can stretch field lines and make them and increase them is feasible for something like the following geometry. So imagine I have a star, and I start out with a seed field, which is like that vertical field I just showed you. And now let's imagine that in the center of the sphere, I have a region which is rotating more rapidly than the surface. Okay, so I'm going to introduce shear where the center is rotating one speed and the outside is rotating at a different speed. Okay, and now you ask, what do these magnetic field lines do which are frozen into the moving fluid? How do they behave in time? Well, what happens is the following. So you sort of think about these guys, and they get advected around because the center is moving more quickly than the boundary. And these field lines just get wrapped up, and you end up with many, many field lines going in the east-west direction compared to the number of field lines that you have going in the north-south direction. So remember, the density of the field lines going through a surface is like the strength of the field, right? And so this is telling you that the strength of the east-west field in this case is many times the strength of the seed field that we started with, okay? And that's the engine that takes rotational energy and turns it into magnetic energy, okay? Now, is this a dynamo? Remember, the dynamo was kind of a feedback, a positive feedback loop, right? I had a seed field, I had currents that flowed in a coil that then reinforced or didn't reinforce the seed field we started with. The same as a feedback loop in audio instability that you have because some sound comes back to the microphone, that kind of thing. Is this a dynamo? Does this have a feedback mechanism in which the dynamo can self-excite? No. It's not a dynamo, and the reason is this field that's being generated is in the wrong direction. It's going in the east-west direction. None of that field reinforces the north-south field that we started with, which was the seed that we fed into the system, right? Okay, so this is not a dynamo. This does illustrate where most of the energy comes from, though, and this is called the omega effect in the jargon, and this is because omega is rotation. And so that's kind of standard physics nomenclature. And it just shows you how shear gives a strong magnetic field. Okay, so this is not enough to be a dynamo, but it shows you where you might get some magnetic energy out of sheared flows in rotating bodies like a star. And the second step, this it turns out it took a long time to figure out. And so, as early as Larmor, people were recognizing that sheared flows could create magnetic fields. It was sort of understood, although not at the detail that we understand it now. And then there was the Dark Ages. And the Dark Ages existed between about when Larmor started and about 1955. And people were actually proving that this was impossible. There were theorems proved which said things like, when the magnetic field and the fluid motions are symmetric about an axis, no dynamo can exist. This is probably the most famous of the anti-dynamo theorems by a person named Cowley. And it wasn't clear how to get around this problem. So the essence of the answer is in this statement. It says when motions are symmetric, it isn't going to work. And so if you started with that simple axisymmetric flow that I showed you before, it can't create its own magnetic field. Now the answer, it turns out, is how do you somehow coax just a little tiny bit of that east-west magnetic field back into the north-south direction to cause the feedback loop to close. And here's how that works. So now let's think about the seed field being that strong east-west field that I just showed you how we create. And let's imagine we have some turbulence, which is like hurricanes moving upward through the convection zone of the sun. The sun's rotating. As these things move upward, there's a Coriolis force which causes them to twist, so that you have some motion outward and some twist at the same time, okay? And now imagine that you have a whole bunch of these in a turbulent region that's taking these field lines, pulling them out and twisting them at the same time. And what happens then is these field lines, they get helically distorted as they get pulled out. And this field, now, you can see is kind of a magnetic field which has the right part. Okay, it's got this, it's got a little bit of a part which is in the north-south direction, and that field is enough to then close the dynamo cycle. Okay, and that closes it, and that's kind of how these systems work. This model, at some level, is a very nice way of thinking about things like stellar dynamos. Usually, there's a convection zone where you have helical turbulence in rotating stars. It works pretty well in systems like galaxies, where you have differential rotation due to Keplerian motion, shearing out magnetic fields in the east-west direction, and then maybe supernovae going off, or other things that cause turbulence in the rotating frame of reference that gives this effect. Okay, and to some extent, that's the status of things. Now, it's much more interesting than that, but we have to talk over dinner. Okay. So this brings me to the final bit of the talk, and we can ask, well, can experiments contribute? And this is a great quote. This is paraphrasing Enrico Fermi. In NHD, one shouldn't believe the product of a long and complicated piece of mathematics if it's unsupported by observation. Some might say that now you can support things with numerics, but I don't necessarily believe that. So, but in any case, experiments still can possibly play a role, and that's where we fit in. Okay, so let's ask first what experiments might require. Now, I've told you that, first of all, I want a big magnetic ground zone. I want a system which I want magnetic fields to be frozen into the moving fluid. And this is a requirement that the conductivity be big, that the flow be fast, that the system be fast moving, and that the system be large enough. Okay? The second is I want to be in a regime in which the kinetic energy of the flowing liquid is much more than the energy density, or if you will, at least we want no magnetic field in that fluid, so we can study where magnetic fields come from, right? And this is a new regime for plasma experiments. Now, why is that? Plasma experiments have been done for 50 years, mostly for things like for fusion research. That's where most of our intuition comes from. In fusion experiments, we have very conducting plasmas, but the reason we have a high conductivity plasma is because we use magnetic fields to provide the thermal insulation that allows the temperature to be high enough so that the conductivity is high. Now, it turns out in plasmas, the temperature, the conductivity is a very strong increasing function of the plasma temperature. So the hotter the plasma, the more like a superconductor it becomes. Okay? And so in hot fusion plasmas, they're essentially superconductors, but they also have strong magnetic fields which allow the plasma to get hot, because that's providing the insulation. And these ideas are basically in conflict. We would like to make a hot plasma without magnetic field, and then to make it even worse, we want to stir it in some way, and stirring is tricky. You can't just stick a paddle into plasma and stir it around. So plasmas are difficult to stir. They require some confinement, which usually requires magnetic fields. And so for the last decade, a little bit longer than the last decade, people have been using liquid metals to study dynamos. Liquid metals like liquid sodium are relatively straightforward to work with. We've worked with them. They're easy to confine. You build a bucket, you pour the metal in, and it sits there. And then you can stir it. You can use a paddle or a propeller, and that works just fine. It's just like all fluids. But there are real limitations that come with liquid metals. And the most important one is that liquid metals are not very conducting. And so the magnetic Reynolds number you can achieve requires a certain amount of power to stir it. And the scaling is that the mechanical power required to get a certain magnetic Reynolds number goes like the cube of the Reynolds number you desire. So we would like big magnetic Reynolds numbers. In liquid metal experiments, you work extremely hard to get enough liquid sodium in one place with enough power to get a magnetic Reynolds number of 100. Okay, and that's not really big enough to study the things we like to study. And this requires over 100 kilowatts of mechanical power to stir it. You want to go to something like 1,000 or 10,000, you're going to require 100 megawatts or more of power, and that's just beyond what you can do in the lab. Okay. Nonetheless, we've been learning things. This is a liquid metal experiment we have in Wisconsin. It's a 1 meter diameter sphere. We fill it with liquid sodium, flows of up to sort of 10 meters per second. We've done a lot of great experiments in this, and we're sort of retiring this now in favor of the next direction. But I'm showing you this because I want to show you the type of experiment we do, and liquids allow us to demonstrate that most easily. So the type of flow that we create in here is essentially two of these cyclones, these hurricanes that you might have in something like a star. So we create those with two counter-rotating propellers that provide thrust out along the poles of the sphere. And because they're counter-rotating, they also introduce rotation, shear, which can produce that east-west magnetic field that we were talking about. Okay? This geometry of two vortices being packed into a sphere is the type of thing that we start with when we design dynamo experiments in the lab. So it turns out that, so these are streamlines. If you sat on a fluid element, you would trace out these trajectories in this liquid, and you can do that with two propellers. This system creates this magnetic field. It creates a dipole field. It might be the simplest possible flow that creates a dipole field. And I'm going to show you this just to illustrate how this works. This is the magnetic Reynolds number on the x-axis. And this is the growth rate on the y-axis for the exponential growth or damping of the magnetic field in this system. And so if the magnetic Reynolds number is 0, if the plasma is not moving or the liquid metal is not moving, this is a decaying magnetic field. As you increase the magnetic Reynolds number by increasing the flow speed or increasing the conductivity, there's a critical point at which it becomes, you get a growing magnetic eigenmode. That's the dynamo we're searching for. It's kind of an instability with a clear threshold in magnetic Reynolds number. And this has a very low magnetic Reynolds number, only about 50. Okay? And the way this dynamo works is understood in terms of stretching of some seed fields in exactly the same way as before. So take a seed field, which is the dipole. It gets pulled out by these propellers. It's stretching, which is the amplification. Okay? And there's a geometry thing here which takes this field line from the center, wraps it back up around the outside, and then it lays it back down in just the right way in the center to reinforce the seed field that you started with, closing the feedback loop that I said was necessary. Okay? So this flow is quite particular, but it's a particularly nice one because it has a low magnetic Reynolds number, it creates a dipole, and it can be created with simple things like propellers. Now, how would we do this with a plasma? Okay? Well, this is the final part of the talk, and I'm going to introduce a little bit of plasma physics. The units change now because plasmas can have flows of tens of kilometers per second, much more rapidly rotating. The size can be comparable. Laboratory experiments are all a meter across. And now I've introduced some plasma physics parameters. So this is the density of the material in units of particles per cubic, 10 to the 18 particles per cubic meter. Okay, and this is So for practical purposes, assume this is 1 in this thing. This is the ion temperature, which might be different than the temperature of the electrons. And these are numbers that you can compute, the magnetic Reynolds number and the fluid Reynolds number. We like plasmas to have high fluid Reynolds numbers so that there's relatively little dissipation by viscosity. And we like the magnetic Reynolds number to be as large as possible, 1,000 or more if we can get there, okay? And to do that requires high density and it requires high temperature, okay? And these are things that we think about in fusion experiments all the time. How do I confine a plasma to make it dense and hot? Those are questions that we have been working on, and is there a way of doing this but without a magnetic field? And we've invented a technique for doing this, and we're studying this in 2 systems, and I'll now describe those 2. So I have 2 experiments that we're working on. One is a spherical system, sometimes referred to as the big red ball. The colors of Wisconsin are red, that's why it's painted red, but this is actually insulation to allow the vessel to be cooled or heated as necessary. It's a big vacuum vessel. It separates into 2 hemispheres, and we create a nearly perfect vacuum inside of it, and we create the plasmas inside this, it'll turn out. This is a system which is somewhat less ambitious in size, but it's addressing disk systems and is looking at questions like accretion onto central objects like black holes, and I'll talk about this. So we have plasmas that we're creating routinely in here with temperatures of 20 eV, so that's like that's 400,000 degrees Celsius, densities of something like 4 times 10 to the 18 per cubic meter. This is almost a perfect vacuum, but not quite, and so it's a very diffuse gas. And flows of things like 10 kilometers per second are regularly achieved. And we're already achieving magnetic Reynolds numbers which are like an order of magnitude larger than in liquid metal experiments. So let me show you how this works. This is the full experiment. You can see a window here. You can actually see inside. There's a plasma here. All of these things are vacuum ports, which allow us to put probes and other objects inside. This is a robotically scanning probe that maps out things like the velocity field and the magnetic field wherever we want to put it, plus we can measure things in 2 dimensions. And these are 2 big Helmholtz coils that allow us to apply a seam field to test various things if the magnetic field is spontaneously created. So if you look through this hole here, this window, along the axis of the device, this is what you would see. You would see these rings, okay? So these are rings looking at the far wall, and these rings are rings of super strong permanent magnets that are covered by a ceramic insulating tile. Okay, so behind, what you see is ceramic, and then behind the ceramic is a strong magnet. I'll show you more about that in a second. And these are rings, and each ring points in the opposite direction. So this is a north-facing ring, this is a south-facing ring, north, south, and so forth. These rings almost perfectly, the magnetic fields of these rings almost perfectly cancel in the center of the sphere. Because we have so many of them, the magnetic field inside the center of the vacuum vessel is non-existent. It goes away, it drops off very quickly. It's a very high-order multipole that drops off. It's a nice Jackson problem. You can show that. So the magnetic field inside here is nothing. It drops off very quickly. And this magnetic field is localized near the surface. It provides a bucket, if you will, for keeping the plasma off the hot wall. So we're cheating a little bit. We're using magnets, permanent magnets, to keep the plasma off the wall so it can be hot. And then mostly what we're interested in is stirring this central region. This forms the core of our star, if you will. And we're going to study how magnetic fields come out of that region. Okay? The plasma, okay, so this is an image on the left. This shows plasma, so it's a big light bulb. This is an argon plasma. It just radiates, there's some light emission that comes out. The losses are restricted to very, very thin lines of plasma loss on the ceramic. So this is like a millimeter of loss. The loss area is reduced from the surface area of the spherical vacuum vessel to a tiny little band because of these strong magnets. And so just by reducing the loss area, when we put some energy in, put some particles in, they don't come out as quickly, the density goes up, the temperature goes up. And so we get a hot, dense plasma by using these permanent magnets, okay? And these are the magnets, okay? And so each of these magnets is a very modern rare earth magnet made of samarium cobalt is the material. These have surface fields on the order of 3/4 of a Tesla, and they just come off the shelf. You think about what a magnet is sometime. You know, magnetic fields created by currents flowing in wires we understand. These things sit there producing a magnetic field day in and day out. You don't need to cool them to cryogenic temperatures like superconductors. They just sit there and they're magnetized permanently. It's quite a remarkable thing, actually. I'm still just baffled by how useful they can be. Now, these rings, they point in and out, and it turned out that you could hand place every other magnet pretty easily. So I could put this magnet in my hand, and then I could put this one in my hand, but if they get too close together, they don't play well, right, because they have forces. And they have over a 250-pound pull force. This is what happens when the two magnets get too close together. So this is a high-speed Phantom 710 camera, 4,000 frames per second. These orbits are fantastic. These are the pieces of magnets that sort of, they go out there, they dance around. It's fantastic. And that's what happens if you're not careful in assembling these magnets inside. So the point is, we had to do something special, and so we could put every other magnet in my hand, and then in between, if you came right down a neutral point where the magnets on either side were providing an equal and opposite force, you could place them just right. So it was a lot of fun for our students to assemble. Okay. Now, we make a big plasma. It's hot, so it's conducting. The final part of the story is somehow how do you stir it. And these magnets play an important role there also. So in the edge, there's a magnetic field that comes in, it sticks out. We take cathodes. Cathodes emit electrons. We put an anode in an adjacent ring, and we drive current across the magnetic field of the pole face of these magnets. We build a DC induction motor in the edge region. We introduce currents that cross the field line. This creates a torque. It causes the plasma to spin. That's all there is to it. It's a DC motor, but in the edge. So what we have is we have the ability to control the flow on the boundary of the plasma. We can control the, my laser pointer is failing, but in the upper, you can see as a function of latitude, by controlling the potential between each of those rings, I can control the rotation as a function of latitude. So I can spin one hemisphere one way, the other hemisphere the opposite direction, and I can control the shear. And this is what we've been doing. So show you the sort of thing. We stirred up in this region here. We measure 10 kilometers per second. That flow penetrates in viscously, coupling momentum to the core, and we're now creating fast-flowing, hot-conducting plasmas. And the next step is to create something like this flow, which mimics the two vortex flow that I showed you. So this is I rotate one hemisphere. This is on the right-hand side is the rotation in the east-west direction. In the left-hand side is we call it the poloidal circulation. This is what gives the vortex. If I spin near the poles, there's a centrifugal force which throws the plasma out. That's what causes the left-hand side to flow. Okay, and this turns out to make a great dynamo. Okay, and I'm just going to show you how this works. This has a critical magnetic Reynolds number of about 300 to self-excite. Okay, this is just solving the magnetic induction equation that I showed you with a solution to the Navier-Stokes equation to govern the velocity field. And we're already creating those types of flows now in the plasma, and we're working on optimizing it to see a dynamo. Okay, I think what I should do is I should stop there, because I think my time is up, right? What do you normally?
You can linger a little bit.
Can I linger just a little tiny bit?
Uh-huh.
I'll tell you the final part of the story. So there's a very, very closely related problem, which is accretion. So accretion is an important process around black holes and protostellar disks, and it has to do with the idea that if you set matter into motion around a centrally attracting object, it stays in a nice stable orbit. If the Earth is not falling onto the sun, it has angular momentum that keeps it from falling onto the sun. Plasma, as it forms an accretion disk, it first starts out as a big spherical mass. It contracts under its self-gravity, and then if it has some angular momentum, a bunch of the plasma is not able to get to the center. So there's this angular momentum barrier that prevents the material from accreting. And it would just sit there way longer than we can predict using the basic properties of plasma that we know, the viscosity and so forth. And so for a long time, there was a question about how is it that matter accretes onto things like black holes. And the answer appears to be related to a special instability called the magnetorotational instability. And I'll try and describe that to you here. And we're studying that in this device, which is called the plasma couette experiment, okay? So the plasma couette experiment is exactly the same as what I just showed you for the spherical dynamo experiment, except it's cylindrical, okay? And the cylindrical nature allows us to think about a couette geometry. Couette flow is flow between two counter-rotating cylinders, okay? So couette flow, I could have an inner cylinder rotating at one speed and an outer cylinder rotating at a different speed. Some velocity profile, the rotation, if you will, is set up as a function of radius, and it depends upon the inner and the outer flow speeds. The center is rotating very fast, it goes one way, and so forth. So you can go from things like solid body rotation, which is the blue line, where the outside is rotating fast, the inside is not rotating very fast, to things like Taylor couette, which is the black line, where the center is rotating very quickly. And if you compare that to Keplerian flow, which is the velocity field for plasma going around something like a star, you can mimic that velocity profile pretty well using couette flow in the lab. Okay? Now it turns out that that flow is stable. There's nothing that happens. It would just sit there stable and nothing would happen if that were all there were to it. But if a magnetic field is present, this flow can be made unstable, and angular momentum can be transported in such a way that matter loses its angular momentum and falls onto the central object. So I'm going to show you a movie of how that works. The rest is just the same. We stir it using cathodes on the outer wall and cathodes on an inner wall, so we make a torus rather than a sphere. We spin the center at one speed and the outer boundary at a different speed. And in this case, you can ask what would happen if you threaded this flow with a weak magnetic field. Okay, so now we're going to do the same frozen in flux movie that I showed you earlier. Let's imagine I have this flow where I have Keplerian-like flow. The center is rotating very fast, the outside is not so fast. And imagine I have a magnetic field which goes through this flow. And now imagine that I perturb the magnetic field where I take the upper point and move it in just a little tiny bit, and I take the outer point and I move it out just a little tiny bit, and then ask how that field line behaves. Well, what happens is the following. So here we perturb it a little bit. Now the center's moving faster, so the inner point is going around more quickly than the outer point. The outer point is moving more slowly, and so what happens is those 2 points start to move away from each other. Okay, they're stretching away from each other. As they stretch away from each other, you can think about magnetic field lines as having tension. So it's acting like a rubber band, if you will, that's pulling the element in the center back. It's allowed to fall to a lower orbit. The element on the outside gets sped up. It has to move to a bigger orbit. And what you're doing is you're allowing the matter, at least on the top orbit, to fall in and accrete. Okay? And so in our lab, what we're doing is we're trying to create this experiment now in a plasma. And that's the final piece of the story. So in summary, there are magnetic fields in the universe. I tried to explain how dynamos work, and we're starting to do experiments which are able to address these questions using plasmas, especially the self-accreting dynamo problem and the accretion problem. So, thank you very much.